Okay, in this video I'm going to talk about the normal distribution. Yes, so unlike kind of similar to the binomial distribution, this one has a larger range of applicabilities. So you have physical attributes such as population, height, weight, arm length, crop yields, scores, and test scores by large populations. A really common one is 2 dice, right? And if you can see here that this would be, it's also, you'll see another term, should be recognizable, is this nice feature that you're seeing right there, also known as a bell curve. That's what the very famous bell curve looks like. So it's actually a normal distribution, and it's an important distribution for continuous random variables, right? And it's a naturally occurring phenomenon that we see, and you can see that where you can actually have these apply. So it's actually quite common, and it's used in a lot of places. So we have this fancy idea of a probability density function, and that's this ugly thing. It's actually, to those of us that, like myself, that worked with quantum mechanics and other things, this is a wonderful function. Just beautiful. It works, and these sort of distributions can be used to calculate with great accuracy the quantum world. So call it the normal curve. The mu is what we call our mean, and standard deviation, which we'll define in a minute, is sigma. So that little dude right there is called sigma, and that is mu. Yeah, and it's kind of made fun of. Mu like a kitten. So there's this. You won't have to know this equation, this really complex equation. You don't need to know it. Because in actuality, you would actually have to integrate this. But you don't do that here. You do that at a much higher level of math later on if you ever choose to go that direction. And most often you don't even need it. So that's what often psychology students actually struggle with, is their stats courses. So that's actually what's being used there. So the mu is our mean. So this is our, like we had with our binomial distribution, this is going to be a norm distribution. The ones that we're going to use on the calculator often are called normal PDF, or more common is our normal CDF. This is the one that we really are going to use a lot more than the normal PDF. But that's the function that we're going to use in the calculator. So what we want to do here is just go over the curve. So there's the nice pretty curve. Again, you will not need to know it, because if you look down here, there's actually where you would need to use your PDF. So this is PDF is probability distribution function, right? Or probability density function. So you actually wouldn't need to do this, but the idea is you have under the curve, your calculator does it for you. It calculates, and all of that is equal to 1. We know that there's a 100% probability something's going to happen, or the event. There is going to be an event. Either, in this case, it could be the complement of the event we're looking at, or the event itself. So the curve, which is a normal curve, is symmetrical, right? So you can see very well that it's symmetric. It's also, x is going from negative infinity. It is going from negative infinities to positive infinities. Again, you get this weird relationship with infinities becoming an important role here. So again, there's our bell shape. each of one is actually talking about a mean, right? So the mean is the central point of a distribution. Standard deviation, what it really just talks about is describing the spread of the data. So you can see that this is narrower than this, which is then narrower than the blue one. And you can think of it like this. Pretty much at high school, so if you go in the terms of b-ball, so basketball, you can think of this as high school. All sorts of players play, so the heights are fairly widely distributed. College ball is a little more selective, so the height selection narrows, and then once you get to the pros, right, or NBA, their height's going to be very specific. So it's a very narrow height range, right? So you see all those tall players, they're in here, right, in that little blue one. However, because of the population density in that is much larger, you have a wider standard deviation, right? That's what they're basically talking about. So it's more common to have a smaller height here as opposed to the pros or college where you're going to have more specific height range. So again, area beneath the curve, that's all what we're calculating, because if you remember, we're looking at it's a function. It's a probability density function, dx. That is equal to 1. Or what we're looking at, this is actually a probability table that you'd actually have to use. But we don't. We're going to actually use our calculators to do that. Yay, us. So, anytime you're calculating area under a curve, well, that'll give you probability. Area is equivalent to probability. Right? This also means that if you look at just the line at 8, if you do it on your calculator, you'll see that they'll give you some probability. But the probability of x equal 8 is 0. Because the thickness of a line, there is no thickness of a line. So the area of a line is 0. So there's a probability of 0 to actually get specifically, let's say, 8 centimeters. Like a plant, you measure it, and you measured hundreds of plants or thousands of plants. You'll never have specifically 8 centimeters. It's 0 probability. Standard distribution. So this is, or standard normal distribution. So this is basically kind of like normalizing we have this, right? So you see the 8, the 10. You'll see that it's kind of redundant and that we don't really need to use it. And I'll show you exactly why in a few examples coming up. But the standard normal distribution is really talking about this idea that the mean, our mu is 0, and our standard deviation is 1, and we call this z. So z values, right? This is the number of standard deviations. And any value is away from the mean. So it just gives you like a distance away from the mean. So if I put this into my calculator, so we'll see here. So you're going to want the function normal CDF, and this is going to be -1. So you do your lower one, upper one, and then you have to put in 0, 1. So you're putting in your mean and your standard deviation. Well, that'll give you 0.6827, which is 68.27% chance that it's going to be within 1 standard deviation of your mean. So really, it's talking about this area right here. That's what it's talking about. So next, we'll do this is standard deviation, and you can see there's our standard deviation, plus the mean and some minus the mean. So what we do again is the normal CDF is going to be minus 2, 2, 0, 1. This will give you an approximately 0.9545, and that would therefore be your 95.45% chance, right? So that's talking about this area. Oops. It's now talking about like this area. So all of it. So it's just talking about that whole span, right? So you're dealing with, there's the first one, then you deal with the second one. And notice that this is what we're going to call a z-score, what we actually talk about just in a second down here. So you'll see our standard deviations, right? So that's one standard deviation right here. One standard deviation, sigma equal 1, right? Oops, same thing here. So we do this again. So if we did the exact same thing, normal, CDF, and this is going to be minus 3, 3, 0, 1. This again is going to give me 0.9973, which is your 99.73%. So that covers this whole thing, right? So your probability of being within 3 standard deviations is 0.9973. This is actually 3 standard deviations is basically testing for theoretical subatomic particles. You actually need 3 sigma within that range, if not a bit better, to have an accurate, that you have measured something like a theoretical particle, kind of like the Higgs boson. Okay, so that's the idea. So our z-score is this, which is just your mean, or the value, sorry, this is value of interest, This is the mean, and this is your standard deviation, standard deviation, right? So that's the idea that we're going to use, and that what we've discussed. So this is our normal, and this is our standard normal distribution. So that's the formula how we're going to use this in the next set of next video, and where I'm going to do all the problems like this. Okay.